Hello. So my name's Andrew Rogers. I'm the Hume Center's resident astronautist. So has anyone seen The Martian? Yeah, so if you're wondering what I do, I'm Rich Purnell. I'm the guy that's like in the back, living on coffee, doing astrodynamics problems. So I'm getting my PhD in aerospace engineering, hopefully finishing up in March, and then getting a big boy job, so we'll see. So you all didn't know that you were going to get a twofer. Bob's going to come up here and tell you about the P3 reboot. Yeah, go ahead and take.
So, as everybody knows, P3E has been in a closet at both of them for years. And ITAR ended the relationship between AMSAT-DL and AMSAT-NA. So, Dr. John Black, who is Andrew's, he and I co-advise Andrew. We went to the United States government and we said to them, hey, look, we've got the spacecraft. It's designed to operate going through the radiation belts multiple times a day, and we don't do very well with rocket motors. And I gave them the entire history and said, we'll take the rocket motor out, you put stuff in, we get amateur radio, you get testing of stuff you need. And in fact, what I believe they have picked is about as exciting as anything I will have ever worked on in my life. And that is the end of what I can tell you about it. Okay, so I went to Germany in July for the Friedrichshafen Hamfest, which is the largest hamfest in Europe. And I met with our AMSAT-DL brethren and said, what do you think? And they said, well, you'll have to come to both of them, which I wanted to do anyway, and talk to the AMSAT-DL leadership and some of the members. So I told them that what is likely to happen, if they give me P3E, is it will come to the United States and go into a closet and they will never be allowed to touch the thing ever again. But that I would not ask them for it unless the government would allow amateur radio on it and operate in the amateur satellite service so that we get another HEO bird. And the directors voted unanimously yes. Then they went, this is a big deal. We're going to put it to the membership, and the vast majority of the membership voted yes, that if the United States government will launch the spacecraft, they will give it to me. John Black and I went to the government. We've had several iterations, and it's the bottom of the ninth. There's 2 outs, and I've got 1 pitch left. And they know what they want to do. And their job is to go sell it all over the body they work for, to test what they want to test, to feel like they can take the smaller sub-elements of the things they want to test, which they are going to build $1 billion spacecraft. And they want me to test the toys that otherwise will be used untested in this $1 billion spacecraft. So I'm the test if I have it right. Okay, so that will be so cool. It'll be really cool. And I'd like to say the taxpayers from wasting their money if I can. And get amateur radio on it. So Andrew's going to tell you some results. You are going to see some things you're going to go, really? And the things he's going to tell you about, you're going to go, really? That's because they're going to exercise the golden rule. Those with the gold rule.
Thanks, Bob. So one of the major issues with taking the rocket out of a spacecraft is it doesn't have a rocket anymore. So we're gonna talk about 2 different approaches to maneuvering the satellite from a 12-hour Molniya type orbit down to a 6-hour HEO. And I'm gonna just you're gonna get a crash course in aerobraking today. That's really the central theme of my talk. So we've got this reduced orbit control capability, and I come from the background of astrodynamicists that do optimal control. So if we can get away with not firing the engine, we're gonna, and that's what we do. So let's talk about that giant orbit transition. This is a huge orbit transition. We're basically cutting the orbit in half. So You got a 12-hour Molniya orbit. It's inclined at 63.4 degrees. The reason is because when it's inclined at 63.4 degrees, the argument periapsis will not precess, according to average orbital element theory. And then, the Russians figured this out, and they did some kind of spooky stuff back in the 50s and 60s with their satellites. But we like this because it gives you a very predictable ground track. Okay, so all right, what happens if you want to try and go from 12-hour orbit down to a 6-hour orbit? You got to do a burn at periapsis. So let's say we've got a periapsis, so the altitude of the satellite that's closest to the Earth, 500 kilometers, and then it's like 40,000 kilometers apoapsis up here. So when you do that, if you want to lower your apoapsis altitude, you need to burn at periapsis, okay? And so if we wanted to do that, just regular impulsive orbit element theory, you're going to need a delta V of 446 meters per second. That is just a ginormous amount of thrust for a satellite that currently does not have a rocket on board. Can everyone see this figure? Trust me, it's awesome, it's there. All right, so we need to come up with a different approach. So there's two different approaches. Let's talk about engines only and then aerobraking, which I learned about how to do about a month ago, so it's fresh in my mind. So if we want to use engines only, let's just throw away the fact that the Earth has an atmosphere. We're going to keep the periapsis altitude at 500 kilometers, and every time it traverses periapsis, you do a quick little burn to lower the apoapsis. Now, if you do it all in one burn or you do it in 1,000 burns, it does not matter. It's still going to take 446 meters per second at delta V. That's just how it goes. All right, so it's a measure of how much fuel you have to use, how much energy you have to eject or take away from the orbit to make that transfer. Now, engine-only maneuvers are great because they can take less time to perform the maneuver. They're a lot easier to analyze, they're a lot easier to model, but they have the kind of massive drawback that they require more fuel. I don't even have a rocket right now, okay? So we need more restricted assumptions on the satellite and on the environment that it's operating in. And then also, like I said, one large burn or lots of little burns, they still equate to the same amount of delta V. Okay, well, let's think about a different way to handle it. So aerobraking has been used to great effect for like Mars missions and other things where they're coming into a planet like Mars just screaming fast, and they want to lower the apogee of the satellite, aposelenium. So this is a more realistic model because now the thing that we're orbiting, the planet, it has an atmosphere, which I can tell you that does. It also has the nice advantage that it allows for a smaller engine to be used. So smaller engine, but you have to trade it off. You're going to have to turn the engine on more times in general. Okay? So, that's nice, what happens, but it does take a lot more time to do the maneuver. Okay? And it can be really hard to predict how long it can take that to do that maneuver. This takes a lot more analysis and modeling, so finding out that it took 446 meters per second at delta V for the engines only maneuver, that took about 30 seconds. This aerobraking thing took me weeks to figure out how to do because I didn't know how to do it. Now, we also have to consider a much more practical issue, which is the structural integrity of the satellite. You're going to be flying through the atmosphere. Satellites are basically made of tin foil, and if you're lucky, they're going to have some strong support trusses in there. But satellites are not made to carry aerodynamic loads. And now we're talking about a satellite that's actually we're going to have to worry about that. So, I'm not solving that problem for you. You just get to think about it. That's for you. Also, we have to consider attitude because the pose of the satellite relative to the incident velocity is going to make a huge difference in how long it takes this maneuver to occur. And then there's the atmospheric model. You know that modeling the upper atmosphere is kind of hard. They've got entire branches of the Navy that are doing this. So in my analysis, I use the NRL MSYS 2000 atmosphere model. If you've ever played with STK, it's a button you hit, you can use it. All right, so we're going to talk about aerobraking now. So this required a lot more analysis. It wasn't just, we'll figure out what the boundary conditions have to be and exactly how much delta V it is. Now we're going to be flying through the atmosphere. So going back to this initial condition right here, this green orbit, This is what we're starting from. All right. So starting from there, on the very first apoapsis passage, you're going to do a very quick little burn that'll lower the periapsis down. Okay, so every time you want to raise your periapsis or lower your periapsis, you have to burn an apoapsis, and vice versa. So we're going to do that. We're going to do a quick little burn. We're going to take the periapsis from 500 kilometers down to 125 kilometers. This is really aggressive. I wanted to just go worst case scenario. Let's see what happens. So we're going to drop it down way deep into the atmosphere where no satellite really should be flying. And then we're going to keep it there. Okay? And so it's going to just start flying around, and every single time it goes through the atmosphere, it's going to pull that apoapsis altitude in. It's going to pull the periapsis in a little bit, but it's going to really drag down the apoapsis. And you can see that. I mean, every single time it comes here, you don't see too much change down here. You see a huge amount of change up here, right? Okay, so I'm a control systems guy. I need to figure out, all right, at some point this thing's going to fall into the atmosphere if we're not careful. So we have a set of orbit corrections that go into it. Say, all right, well, it started at 125 kilometer altitude at periapsis, so every time it goes through, it's going to keep lowering that periapsis a little bit. It's going to really help the apoapsis, but eventually it's going to go too low, and we're not going to be able to do anything about it. So what we said was, well, if we just do a quick little kick every time the periapsis altitude goes down below 100 kilometers, that'll save the satellite, and it won't change the actual orbit too much. So we did that. Okay? And so it just keeps going down, and then we go down to the point where the satellite gets into that 6-hour sweet spot orbit that we wanted it to be in. And so we calculated this takes about 169 days. Now, there's a lot of assumptions that go into this. So it could be anywhere from 140 to 200 days to even a couple of years if you play around with the parameters. Orbits are notoriously chaotic. They're notoriously hard to predict over long periods of time. So, this will give you kind of a ballpark of how much delta V you need, but, I mean, it's a fiction, ultimately. But more importantly, I said with engines only, it's going to take 446 meters per second of delta V to do that transfer. Well, now we're looking at 115 meters per second of delta V, doing this aerobraking maneuver. Your jaw should be coming up off the floor now because this is a huge win for us. We've got no engine, basically, and now we can do a massive orbit transfer using the atmosphere as the controller. Okay, that's really cool. All right, so then once we get down to that 6-hour orbit, we need to make sure we do a couple quick little corrections to make sure that it's actually in the 6-hour orbit that we want, and that gives you your 115 meters per second delta V. So this is very sensitive to the periapsis altitude. So for instance, the first time I tried playing around with it, I set periapsis altitude to 150 kilometers, so 125, 150, and let it go down. It took 4 years, all right? Yeah, wow. So, when someone goes in to do these trajectory analyses, there's a lot of things you have to consider. I mean, there's hundreds of parameters, and you're just seeing some of the ones that I thought gave good results to make us look good. So, I guess the major issue with this aerobraking is, large fuel savings, but at a price, and that price is time. All right. So now we're in our nice 6-hour orbit that we want to be in, so now we need to start doing orbit maintenance. So the way we do this is we say, well, I've got some box of initial conditions that I want to stay in, okay? So I set up some bound on my periapsis and apoapsis altitude, eccentricity, inclination, argument periapsis, all the orbital elements that I like to think about, and I do like to think about them. So I've got some nominal set that I want to maintain, and then I just let it go. I've turned on every single perturbation that's in Satellite Toolkit. I've got the entire solar system. I've got a high-fidelity atmospheric model. I've got the WGS-84 Earth model. I've got, solar flux, geomagnetic flux. I got the tides. I've got everything, all right, because I can. It was awesome. And then we just let it go forward for 3 years, just, because I picked 3 years. It can be as long as you want it to be. And so the things that we need to correct are, we need to correct the argument of periapsis. So, in the ideal case, you set it to 63.4 degree inclination, the argument of periapsis isn't going to change. Well, that's only for the J2 perturbation, the kind of fat donut running around the Earth's equator. You add in other stuff, that number changes, and it's impossible to figure out exactly what it's going to be. So, the argument of periapsis is going to change. The inclination is going to change a little bit. And we don't want it to change too much, because if the inclination changes, then the argument of periapsis changes, and we don't have a mission anymore. Yeah. And then furthermore, you're flying through some atmosphere at 500 kilometer altitude. You gotta correct when it gets down too low. So, with these 3 orbit control algorithms built into it, and then just letting it go forward, we predicted 100 meters per second delta V for maintenance over the next 3 years. Now again, when we go to actually do this, this is subject to change. This is just based on the information that I had. But you can see, if you calculate all of the perturbation mitigation controllers, and you calculate the aerobraking, we are still about 1/3 of how much fuel we needed for just to do the engines only orbit transfer. That's a huge win. All right, so this can be done. You put a little rocket on there, you can do these things. Okay. All right, so I'm going to show you a couple quick graphs just to kind of give you a flavor of some of the stuff that I've been talking about. So this is the graph of the apoapsis altitude versus time for that aerobraking maneuver. Okay, and I told you the apoapsis is going to fall. I gave you a graphic that shows the apoapsis is going to fall. Well, it did. Okay. All right. More importantly, periapsis, which is where it's closest to the Earth. This is where that orbit controller really came in handy. So during the apoapsis shift maneuver, so we're trying to pull the satellite down. If you can kind of see down here, you'll see that the periapsis would fall and then it'd jump back up, and it'd fall and jump back up. So every time it got down to 100 kilometer altitude, I said, all right, go to apoapsis, give it a quick little kick, shove it back up to 125 kilometers, and then turn it off. Turn the engines off. I don't want them on. All right, so that's what's happening. We're looking at a couple different little maneuvers to push the periapsis altitude up so it doesn't fall into the Earth, which we can all agree is a good thing. And then once it gets to, once the satellite has pulled the apoapsis in enough, we have to shift it back up so it's got a 500 kilometer periapsis again. Because we don't want this thing down at 125 kilometer periapsis for 3 years. That's way too much fuel. I mean, that doesn't make any sense. So once it's up here at 500 kilometer periapsis, there's a couple quick little burns, and you can make this as coarse or as fine of a control adjustment as you want. This is up to you as the users to figure out what you want to do. But so, it doesn't, in general, the engines are not on. I mean, this thing is barely ever turning on its engines, and that's a big win for us. Here's eccentricity. I mean, if your periapsis is the same and your apoapsis is changing, the eccentricity is changing, so that's all I have to say about that. Now, inclination. I predicted you only needed one plane change maneuver to correct the inclination, and that's good because inclination is extremely difficult to change. And in fact, so the reason the Russians like using Molniya orbits is because where they launch from Kazakhstan, they want to get down to the geosynchronous belt to keep their satellites there. It's actually more fuel efficient to go to Mars than it is to go to geosynchronous. Come on. That's ridiculous. All right. So this is just a quick little burn here to correct a, let's see, 1/4 degree change in inclination. We only have to do it once, and we expect that. We want to try and minimize how many of these we have to do. And then correcting the argument of periapsis. This thing's going to be perturbed for 3 or 4 years. It's going to have to get changed eventually. So we found that we only needed 2 periapsis corrections. Argument of periapsis. All right. So I've told you about aerobraking. I learned about aerobraking about a month ago. It was totally awesome. And all this analysis leads me to believe that you probably don't have to put a very big engine on board P3E when you go to launch it. So we've got very sparse engine activity, and you want that since you currently don't even have an engine. And so there's room for additional optimization. So that's all I've got. I'll take your questions now. I'll start with you.
What kind of engines are you going to have on the spacecraft?
No idea. Sorry, I don't know.
I'm totally confused.
Okay.
As I understand that the satellite will originally be put into a 12-hour going in orbit.
Yes.
Number one, why do we want to change that? It seems like it's a pretty good
Keep
orbit.
with the gold rules.
I thought you were going to say that, Bob. So, okay, we're being forced to change it because of other circumstances. I guess I understand that. Are we concerned about the heating problem when we're doing the aerobraking? That's the other thing that worried me a little bit.
Potentially. So this is something that I'm going to have someone that knows a lot more about heat transfer than me figure out, because that's highly sensitive. The amount of thermal heating is highly sensitive to your periapsis altitude. So if you set that periapsis altitude really low, you're going to have to really worry about it. I think at about 125 kilometer altitude, you're only actually in the really dense part of the atmosphere for maybe 4 to 5 minutes. I mean, you're going like 18,000 miles per hour here, so it's not lasting that long, but it could be an issue. So maybe.
Can you see how many G's do you expect to cool that periapsis?
You're going to be, I don't know, geez.
That's your business.
I mean, you're not going to notice too much slowdown during
Well,
periapsis.
it's a question of acceleration, just,
So,
drag.
If
you don't know the answer, that's fine.
yeah, I have no idea.
Almost facetious, but not really. You worry about orbital collisions with space debris?
Not
Yes.
moving at that speed. If it does, we're obliterated.
You should always be worried about orbital collisions.
I just thought you're dipping in and out a whole lot in the course of this. And you're getting even closer to the Earth where there might be...
Well, it's twice a day, and then down to 4 times a day at the end.
I'm just wondering how much space weather and so on has effect on the size of the atmosphere, and whether you have any warning, or how much warning you will have.
Not that much, and it has a huge effect on it. So that's one of those things that you can kind of build a probabilistic model, and that's what Systems Toolkit does. I learned how to use STK when it's still Satellite Toolkit.
So right now,
It looks like we're going to go in 2018-ish, so that's well off the peak of the sunspot cycle, so we will be going in happy circumstances.
That's right here. Yes.
Is there a preliminary estimate on satellite lifetime, usable lifetime?
So that all depends on how much fuel you carry. If you just turn off the engines and just let it go, you're looking at about 15 years to decay down. And that's a very conservative estimate, though. So that's, I assumed that when it was flying with the kind of the largest profile of the satellite going straight into the atmosphere at a solar peak. So it could be 15 years, it could be 30 years. And so you want to carry enough fuel so you don't have to worry about that. So you can graveyard it if you need to. Yes?
Sounds like they're doing this to maximize radiation exposure on the test items.
there are dosimeters all over it under their plane.
Okay, well, what effect is the maximized radiation going to have on satellite lifetime?
I don't know. Yes.
So during one of those maneuvers, when the engine fails, or if the engine fails, then how long does it last? Days, months?
Well, which maneuver? There's 32 maneuvers in this.
Okay. Worst case, you lose it. You get down to 100 kilometers at the bottom, and the propulsion system fails.
You're not going to stay up there too long.
I mean, like days, weeks, months.
Weeks, maybe.
Okay.
We have some experience with that in
AO13.
Yes.
Yeah.
Okay, that's it. Very good. Thank you.